Hello my dear students, good morning to you all. So, in my last class I was explaining about Schrodinger wave equation for hydrogen atom. So, the conclusion of Schrodinger wave equation for hydrogen atom was, so it gave, that is the Schrodinger wave equation gave a hydrogen atom yield 3 wave functions and which were called as radial wave function, and also so by using this Schrodinger wave equation for hydrogen atom yields 2 quantum numbers. So, that is n and L. So, there n is analogous to principal quantum number and L is similar to Azimuthal quantum number of Bohr-Sommerfeld theory. And also by solving Schrodinger wave equation of hydrogen atom, so we deduced expression for energy of an electron in hydrogen atom, that especially, and that expression it gave the values of energy which was corresponding to different value of n, and where n can have the integral values, that is integral values means n is equals to or n can be 1, 2, 3, 4 etc. like that, and the energy of the electron depends only on its distance from the nucleus. So, this is what we understood by studying the Schrodinger wave equation for hydrogen atom, which was understood in my previous class. So, in this session, so let us understand what is meant by quantum numbers, that too with respect to the Schrodinger wave equation for hydrogen atom. So, where in the conclusion part just now what I told, so the Schrodinger wave equation for an hydrogen atom yields 3 quantum numbers, that is n, L and m. So, what are these quantum numbers? So, mainly a quantum number can be understood as the set of numbers which were used to describe the position and energy of the electron in an atom are called quantum numbers. So, this is a general issue or general understanding of quantum numbers. These quantum numbers gives us the information about the position and also the energy of an electron in an atom. So, if we know the structure of the atom, so then it will be very easier for us to understand what exactly it means. So, according to the structure of atom, what we have understood in our lower classes, an atom consists of an atomic nucleus. So, that is the center of an atom which constitutes positively charged particles which are called as protons and uncharged particles which are called as neutrons. So, these two both, that is protons and neutrons, they constitutively forms atomic nucleus, and protons are positively charged as I said, and it contributes a charge of the atom. And what are electrons? So, electrons are the negatively charged species which revolve around the center of nucleus. Larger region which is composed of a cloud of negatively charged particles are called as electrons. And what are neutrons? So, these neutrons are scattered particle which are used to calculate mass of the neutral particle. So, this is a general structure of an atom, and these quantum numbers are the set of numbers which are used to describe the position and energy of the electron. It speaks about electron, in which orbital the electron has been situated or located, and what is the energy of that particular electron which is present in an atom is understood by studying these quantum numbers. There are 4 quantum numbers, namely principal, azimuthal, magnetic and spin quantum numbers. So, these are the main 4 different types of quantum numbers. So, these 4 quantum numbers can be used to completely describe all the attributes of a given electron belonging to an atom. So, usually principal quantum number is denoted by small letter n, orbital angular momentum quantum number, or it is also called as azimuthal quantum number, it is denoted by small letter l, and magnetic quantum number is denoted by small letter m, and the electron spin quantum number is denoted by small letter s. So, what are the possible values for these 4 different quantum numbers? So, usually principal quantum number can have all the integral numerical values, that is 1, 2, 3, 4 etc. Angular momentum quantum number can have 0, it also possesses or exhibits 0 possible value, or 1, 2, 3 up to n minus 1, and magnetic quantum number will be between, or it might be a negative. So, minus L, starting from minus L or minus 3, minus 2, minus 1, 0 or 1, 2, 3, 4 up to L. So, these are the possible values which a magnetic quantum number can take, whereas the spin quantum number, so it will have either plus half or minus half. So, these are the different possible values which the quantum numbers can take. So, now let us see briefly one by one what is meant by a principal quantum number. So, as I said, it is denoted by small letter n, and it determines the energy of the electron and average distance of an electron from the nucleus. So, the principal quantum number defines, or it gives us the information about the average distance of an electron from the nucleus. And as I said, so it can have all integral values. As n value increase, the electron gets farther away from the nucleus and its energy increases. Next is azimuthal quantum number. The energy of an electron is also associated with its orbital motion around the nucleus. So, it does not only depend upon how far or in how much distance it has been located, but it also depends upon the orbital motion around the nucleus. So, that is why there exists orbital angular momentum quantum number. So, this describes the shape of the given orbital, and it is denoted by small letter l, as I said, and its value is equal to total number of angular nodes in the orbital. A value of the azimuthal quantum number can indicate either an S, P, D or F subshell which vary in shapes. This value depends on the value of principal quantum number, that is the value of the azimuthal quantum number ranges between 0 and n minus 1. So, the orbital motion is described by the angular momentum of the electron, which is characterized by azimuthal quantum number. The value of L gives the subshell in which the electron is located and can have values 0 to n minus 1. So, these subshells are S, P, D and F subshells, and it also determines the shape of the orbital in which the electron is located, and it also determines the shape of the orbital, and the L can have values from 0 to n minus 1. And next is the magnetic quantum number. The total number of orbitals in a subshell and the orientation of these orbitals are determined by magnetic quantum number. This number, that is magnetic quantum number, yields the projection of the angular momentum corresponding to the orbital along a given axis. The magnetic field which is produced by the orbital motion of an electron can interact with an external magnetic or electric field. So, as a result, there is an interaction, that is the electrons in a given energy sublevel orient themselves in certain specific regions of space around the nucleus. So, these regions of space are called orbitals. So, here we can understand what is meant by orbitals. So, as I said, since the magnetic field produced by orbital motion of an electron can interact with an external magnetic or electric field, due to this phenomenon, so there happens interaction between the electrons which is given by the sublevel orientation having themselves to orient in certain specific regions of space around the nucleus, and these regions where the electrons can revolve or where the electron they themselves create an energy sublevel which is called as a specific region of space around the nucleus, and these regions of space are called as orbitals. The number of values or the number of orbitals in a given energy sublevel within a principal energy level is given by the magnetic quantum number. So, here comes the importance of magnetic quantum number. So, the magnetic quantum number helps us to find out the principal energy level by using the number of orbitals in a given energy sublevel. So, within a principal energy level, it is given by using the concept what is called as magnetic quantum number, and it is denoted by small letter m. And the values of or the number of values allowed to m depends on the values of L, m, and can have values from plus L through 0 to minus L, thus making a total of values 2L plus 1 values. So, the value of magnetic quantum number is dependent on the value of azimuthal quantum number. For a given value of L, the value of m ranges between the interval minus L to plus L. Therefore, it indirectly depends on the value of n. N is principal quantum number here. So, next is about spin quantum number. The electron spin quantum number is independent of the values of n, L and m, that is principal quantum number, azimuthal quantum number and magnetic quantum number. Spin quantum number is independent of all these three quantum numbers. The value of this number gives insight into the direction in which the electron is spinning. Okay? So, this is what the information the spin quantum number is going to give. So, it gives or the value of this spin quantum number is the insight into the direction in which the electron is spinning. The value of S, that is the spin quantum number, offers insight into the direction in which the electron is spinning, and the possible values of the electron spin quantum number are plus half and minus half. So, electron spins on its own axis. So, due to spinning of electrons, they possess an intrinsic angular moment which is called as spin quantum number, and it is represented or denoted by small letter s, and it can have the values of plus half or minus half. So, this is all about the four different types of quantum numbers, and in this so the Schrodinger wave equation, it gives a solution for a Schrodinger wave equation for hydrogen atom, and which yields three quantum numbers, that is n, L and m. And next is about quantum numbers and electron accommodation. So, how the electron accommodation is going to take place? So, usually we know that the electron accommodation is based on the postulate of Niels Bohr, that is electrons revolve around the center of an atom, that is nucleus, in a predictable pathway which is named as orbits. The representation of the orbits is done by letters and numbers such as K, L, M, N, O and 1, 2, 3, 4 respectively. So, the arrangement and distribution of electrons in different orbit was given by Bohr and Bury. Usually, the arrangement of electrons in different shells and subshells is known as the electronic configuration of a particular element, and the electronic configuration diagram represents an element in its ground state or stable state. So, there are a set of rules to remember while distribution of electrons in different orbits. So, this table gives us the information about the quantum numbers, okay. The quantum numbers also along with these quantum numbers, so we can see the electron accommodation based on these quantum numbers. So, here in this table, so the first row it speaks about principal quantum number, and principal quantum number it is denoted by small letter n, and it is given by the number, either the number or alphabet, that is just like how I have said now, K, L, M, N or 1, 2, 3, 4 respectively. And here the shells begin from the center and gradually move outwards. Okay, so this we should observe. So, K shell will always have minimum energy. So, that is why it is having 1, principal quantum number is 1, and it is having minimum energy. So, that is why 0, and magnetic quantum number is also 0, and spin quantum number is, it can be either plus half or minus half, and number of electrons in subshell is 2. Similarly, L shell is a little away from the nucleus, so it will have higher energy than K shell, and the outermost shell will have maximum energy. Now, it is important to understand the distribution and arrangement of electrons in the atoms of any elements in the different energy levels. An atom of any element is most stable when it is having minimum energy. An atom will first fill the lowest energy level so as to attain the state of minimum energy. Gradually, the electrons will fill the higher energy levels. Therefore, electrons will first fill K shell, then L shell, then M shell and N shell and so on. Okay, so that is why if we see here, so depending upon the electronic configuration also, if we observe the azimuthal quantum number, so here, so 1s is the subshell, and in 2, that is principal quantum number 2 or L shell, so 2s subshell or 2p subshell is possible, and if we move on to M shell, 3s, 3p and 3d subshell is possible, and if you move on to N shell, so there 4s, 4p, 4d and 4f are the possible azimuthal quantum numbers which we can observe. In the same way, so the magnetic quantum number also differs. So, since K is the lowest shell, okay, so the electron will first fill the K shell, so there we find no magnetic quantum number, so therefore it exists 0 magnetic quantum number, whereas as it proceeds, so the L shell or in the L, so the magnetic quantum number takes up either positive, that is plus 1 or 0 or minus 1. Okay. And next, if we move on to this spin quantum number, so here in all cases, since 2 electrons are the possible chance of accommodating in these K, L, M, N shells, so it will have 2 number of electrons in a subshell. So that is why spin quantum number can either be plus half or minus half. Okay. So this is how, so we understand the quantum numbers and electron accommodation. The quantum numbers used to refer to the outermost valency electrons of the carbon atom, and which are located in the 2p atomic orbital, are n is equals to 2, that is second electron shell, and L is equals to 1, so that is a p orbital shell, and M is equals to plus 1 or 0 or even minus 1, whereas so the spin quantum number, so that is S will be equal to plus half or minus half. So next is about comparison of classical mechanics and quantum mechanics. So now we are at the end of this chapter. So what are the differences or what are the comparison between classical mechanics and quantum mechanics? This we also have studied in the earlier classes in the beginning. So to understand what are the importance of quantum mechanics, what is the necessary or what is needed, why the quantum mechanics developed, so there we understood. So due to the drawbacks or where the classical mechanics failed, where the limitations of classical mechanics was seen to study various different concepts of physics as well as chemistry, that is black body radiation or photoelectric effect. So, many things were not explained, or Compton effect. So, all these were not explained properly by taking or by considering classical mechanics, whereas so the quantum mechanics gave a clear explanation for all these phenomenons, including black body radiation, heat capacity of solids, photoelectric effect, Compton effect, etc. So, now let us see what are the main comparison of classical mechanics and quantum mechanics. So, classical mechanics deals with macroscopic particles such as planets and rigid bodies, whereas quantum mechanics deals with microscopic particles such as electrons, protons, atoms and molecules. Classical mechanics is based on Newton's law of motion, whereas quantum mechanics takes into account the Heisenberg's uncertainty principle and de Broglie's concept of dual nature of matter. Classical mechanics is based on Maxwell's electromagnetic wave theory, according to which any amount of energy is emitted or absorbed continuously, whereas quantum mechanics is based on Planck's quantum theory, according to which only discrete values of energy are emitted or absorbed. The state of system is defined by specifying all the forces acting on the particles and also the position and velocities, whereas the state of system is defined by wave function psi, and it gives probabilities of finding the particles at various locations in space. So, these are the four main comparisons of classical mechanics and quantum mechanics. So, this completes this chapter, that is quantum mechanics or elementary quantum mechanics. So, in my next class we will start with another new chapter. Thank you, dear students.